Hi, Margaret. I wanted to give you a short little video about acids and bases. They showed up on your last exam, and I think you'll probably have to see them again. And so I thought I'd mention a little bit about what they do when they get put into water and how they react with each other. You can see here on the left, I've written a list of 6 different strong acids. Those are the ones that we make our students memorize. I'm not sure what they do at Wisconsin, but they probably do the same as well. So I'll just pick HCl as the first example. They all do exactly the same thing. And so if you know that it's a strong electrolyte, that essentially means that it completely dissociates when it goes into water. I didn't put little AQs on here, but I think you know what I'm talking about when I do that. Strong bases kind of obviously just dissociate if they're soluble. So if you look at your list of solubility rules, you'll see that a lot of the hydroxides are insoluble, but some of them that are do this. So they just completely dissociate. One thing I want to mention, sometimes you'll see calcium hydroxide listed as a strong base, but this is barely soluble. So that doesn't mean that it can't react, but you should just know that it really doesn't go into water very easily. When a reaction occurs between these, it's a really straightforward reaction. So I'll just pick one of the strong acids, HBr, and I'll pick one of the strong bases, NaOH. And you've probably heard of this before as a neutralization. The thing about these reactions is they're just like the exchange reactions that you've seen before, where you take the cation of one side and the anion of another. And look what happens. So if I take sodium with bromide and then I look on my solubility table, I'll get NABR, which is soluble. The cation from the acid and the anion from the base basically form water, and we write that just as a liquid. The fact that this is soluble, totally soluble, means that the net ionic equation, which is the one that removes the spectators, is simply this. The H plus the OH minus goes to H2O. Okay. If you look up at the top of this page, every single monoprotic acid, so the 5 that I just checked off, and every single one of the monobasic salts has exactly the same net ionic equation. And the reason is because these cations and these anions, they're basically all spectators, so they don't even appear in the reaction at all. Some complications occur a little bit if I were to use, let's say, this barium hydroxide. So if I mix, let's say, HBr with barium hydroxide, notice that the stoichiometry is going to change a little bit. I'm going to need 2 HBRs for every 1 BaOH to give, in this case, BaBr2. And if you look at your solubility rules, you'll see that that's soluble. And I get 2 waters over here. If you go through to the net ionic equation, you get something that looks like this, which I don't take off if my students write this, although you probably should divide everything by 2 just to get through that. But this is an example of a neutralization, and these are actually the type of reactions that go on in titrations. So in a titration, usually you have some kind of liquid. I'll do a terrible job of drawing a flask here. And let's say, for example, it is, I'm told ahead of time that it's HBr. But I don't know what the concentration is. I don't know what the molarity is. And I'm going to titrate it by reacting it with sodium hydroxide, let's say. And let's say they tell me they do know the molarity. Let's say it's 0.250 molar. If it took, let's say, if I had 50 mLs of, you know what, I'm going to change that. I'm going to change that because that's not usually the way they write it. Let's say I had 50 mLs of this acid, and it took 28.5 milliliters of the base to neutralize. can you figure out what the molarity is of the acid? And for any titration problem, you need to know what your reaction is. And this is one that I actually kind of implied on the previous slide, that if I get this here, I have a soluble salt. This is a 1-to-1 ratio with moles. So if I know the moles of the NaOH, I know that the number of moles of the HBr will be exactly the same. So let's figure out the moles of the NaOH. So you might recall, I'll do this on the side, that if you have the molarity of something, that's how many moles there are per liter. And if you multiply that times a volume, which is usually in liters, you end up getting moles. So for the NaOH, I'm taking 0.250 molar NaOH times the volume in liters, 0.0285 liters. And Dr. Check brought his calculator here. Let's see what I get. 0.250 times 0.0285. Oh no, I hit the wrong button. Times 0.0285. I have 0.007125 moles of NaOH. Now, since the HBr has to be exactly the same because this is a 1-to-1 ratio, this also means I have 0.007125 moles of HBr. What's the molarity, you ask? That's what the question is. Well, I'm going to take that moles and divide by the volume in liters, because we know that moles per liter is a molarity. And so I finally get a number of 0.050, 0.1425. So that's how you do a titration problem for an unknown strong acid. Hope this helps. Bye.